In the last video, I made a claim that any terminating or repeating decimal represents a rational number. And then, of course, any decimal that doesn't terminate or repeat represents an irrational number. So in this video, I'm going to give you kind of a demonstration of this. These are not proofs because I'm only showing this for specific examples, but this can be done in general. The notation gets a little bit wonky. But this is not just because the math teacher says so, right? The structure of the numbers means that any fraction is represented as a terminating or repeating decimal, and any terminating or repeating decimal can be represented as a fraction. So to show that every fraction can be represented as a terminating or repeating decimal, we just do decimal long division, right? So remember, for example, 5/8 represents 5 divided by 8. We can set up long division with a division bracket with the 8 on the outside, the 5 on the inside. If it's been a while since you've seen long division, don't worry, just try to follow the structure of the argument. So 8 goes into 5 0 times. We copy the decimal point. 8 goes into 50 6 times, because 6 times 8 is 48. We subtract 50 minus 48 is 2. Bring down the next digit is 0. 8 goes into 20 twice, because 2 times 8 is 16. We subtract again. 20 minus 16 is 4. Bring down the next digit, another 0. And then 8 goes into 40 5 times, because 5 times 8 is 40. We subtract, and we have no remainder. So this is a terminating decimal, because as we did that decimal long division, we ended up with nothing left. So 8 can't go into this anymore. If we kept adding more digits after this decimal point, they would just all be zeros. 19/22 is going to be a repeating decimal. To see that, we do the same decimal long division. So 22 goes into 19 0 times. 22 goes into 190 8 times, because 8 times 22 is 176. 190 minus 176 is 14. Bring down the 0. 22 goes into 140 6 times, because 6 times 22 is 132. We subtract. 140 minus 132 is 8. Bring down the 0. 22 goes into 83 times, because 3 times 22 is 66. We subtract. 80 minus 66 is 14. And at this point, we notice something. This remainder 14 has just been repeated. So that means I'm going to have a 14, bring down a 0 and get 140, which 22 will go into 6 times, which then is going to give me a remainder of 8. Bring down a 0, I'll have 80, which 22 is going to go into 3 times. So at this point, my remainders are going to be stuck in this loop of 14 and then 8 and then 14 and then 8, which means that the digits in my decimal are going to be stuck in this loop of 6 and then 3 and then 6 and then 3, and that's going to keep happening forever. So every time we try to convert a fraction into a decimal, one of these two things is going to happen. Either we'll get to a point where we have remainder 0 and then the decimal terminates, or we'll get to a point where the remainder is repeated and then the decimal repeats. Every rational number, every fraction that is, when we write it as a decimal, will be either a terminating decimal or a repeating decimal. What about the other way around? How do we know that we can write any terminating decimal as a fraction? Well, we know that because we have a method to figure out what the fraction is. The denominator is always a 1 followed by however many digits there are after the decimal point. So 1 followed by 3 zeros. So 3 digits after the decimal point means I'm going to have a 1 followed by 3 zeros. And then the numerator is just whatever number we see if we ignore the decimal point. So in this case, 385. We can write 0.385 as a decimal, 385 1,000ths. Now that's not in lowest terms, right? Our numerator and denominator, they have a common factor of 5. We could simplify this fraction if we felt like it, but we don't have to. In order to know that this is rational, we just need to be able to write the number as a fraction. We don't have to worry about simplifying for this purpose. So every terminating decimal can be written as a fraction because in a sense that's just what the notation means. What about repeating decimals? Well, we can use some algebra to show this. Now again, I'm going to use a specific example. I'm going to show that 0.87 repeating can be written as a fraction. But again, we can do this for any repeating decimal. I'm also going to use a little bit of sleight of hand in this algebra, but if we're more precise about what the repeating decimal means, we can be more precise about what's happening in this algebra. So what I'm going to say is, I'm going to create a variable, and I'm going to say, let x represent the number we're interested in, right? 0.87 repeating, which means 0.87, 87, 87, etc. Right? Okay, what can I do with that? Well, if I have two numbers that are equal, I can multiply both sides of that equation by any number I want, and they'll still be equal. So let's say I want to multiply both sides by 100. So then 100x is 100 times 0.87, 87, 87, etc. When we multiply by 100, we move the decimal point 2 places to the right. So I have 100x equals 87 point, and then the pattern 87 repeats forever. So 0.87, 87, 87, etc. Okay, and now I'm going to do a trick. I can subtract the same number from both sides of an equation. I'm going to subtract the number x from both sides of this equation. But on the right-hand side, I'm going to write the decimal that x is equal to. On the left, I have 99x. On the right, well, I've got 87 point a bunch of 87s minus just a bunch of 87s. And notice that in every place, I have the same digit. So just think about the way we do long subtraction. When I subtract down the columns, I'll be doing 8 minus 8, or 7 minus 7. I'm going to end up with 87.000000, etc. In other words, 99x is 87. Dividing both sides by 99, I get x is 87/99. But I started out by saying x was 0.87 repeating, so 87/99 must be 0.87 repeating. And again, this is a game that we can play with any repeating decimal. If we have a more complicated pattern, this game gets a little bit more complicated, but any repeating decimal we can rewrite as a fraction using this method, which tells us that any repeating decimal can be written as a fraction. Now we know anytime we look at a decimal, if it terminates, that's a rational number. If it repeats, that's a rational number. If it does either one, then that number is irrational.